morning everyone, hope you're fine today. Our continuation of the lesson is going to be about resonance circuit analysis. We're going to study it in two methods: resonance experimental analysis and resonance theoretical analysis. And using these two methods, we're going to find out what is resonance. First of all, we're going to study this curve, and we have the current versus the proper frequency. So we have measured the current versus the proper frequency, which is omega, and we realized that at one point, which is at omega 0 here, we realized that omega 0 corresponds here to a maximum current, which is almost 0.5 milliampere for the green curve, and omega 0 corresponds to 1 milliampere for the blue curve, and omega 0 corresponds to 1.4 milliampere for the brown curve. Based on that, we realize something else, that at these points we have maximum currents for the three curves respectively. So this means that we have U and I are in phase. If U and I are in phase, this means that phi is 0. So in this case, the RLC circuit behaves like a resistive circuit. However, that's interesting to know as well, that as the curves go up until reaching the resonance frequency, we realize that I leads U, and in this case RLC circuit behaves like an RC circuit. However, when these curves are going down, we realize that U leads I, which means that the RLC circuit behaves like an RL circuit. That's very interesting actually. Based on that, let us define resonance. Resonance is actually the physical phenomena that occurs for a maximum current at almost the same frequency, regardless of the value of R. And here we realize something, that R here is 3.5 ohms, and here is 5 ohms, and here is 10 ohms. So as the resistance actually increases, we realize that as the resistance increases, the current, maximum current, is actually decreasing. So I and R are inversely proportional. Based on this, as R decreases, the curve becomes narrower and taller. So vice versa, R decreases here. So if R decreases from 10 to 5 to 3, we realize that the width here becomes narrower. So the frequency actually is becoming narrower and narrower, until when R is actually 0, which does not exist in real life, but theoretically this means that the frequency will be infinity. But of course in real circuits we always have some resistance. Now for the resonance theoretical analysis. Tangent phi is L omega 0 minus 1 over C omega 0 over all over R is equal to 0. That's when we have resonance, because if phi is 0, this means that tangent phi is 0 as well. So based on this, L omega 0 minus 1 over C omega 0 is equal to 0. Based on that, L omega 0 is 1 over C omega 0, and based on that cross multiplication, we have LC omega 0 squared is equal to 1, and now we can find omega 0, which is 1 over LC. Based on that, we know that omega 0 is 2 pi f of R, the resonance frequency. This implies that LC times omega 0 squared. So omega 0 is 2 pi of R squared is equal to 1. So I'm just substituting in this equation. Is equal to 1 implies f of R squared is equal 1 over, this is actually squared, okay, LC. So this implies that 2 pi will go out, it will be 1 over 2 pi square root of 1 over LC. So that's the resonance frequency equation. And then we can find the period, because the resonance frequency is 1 over the period and the period is 1 over resonance frequency, so it will be 2 pi square root of LC. Of course, that's in second, and that's in hertz or cycles per second or turns per second, and of course omega, it's in radians per second. Now I'm gonna give you a note which is very important. Whenever we have a phasor diagram for a pure resistance, a pure inductance, and a pure capacitance, this will happen. So that's the voltage of the resistance, which is actually here. It is in phase with I, and that's the voltage of the inductor, which makes a 90 degrees angle with the current. And we have the voltage of the capacitance, also makes a 90 degrees. What's the difference between the capacitance and the inductor? In the capacitance we have a negative 90 degrees, minus pi by 2. And here we have plus pi by 2, which is the phase angle between them. Now let's go for the practice exercise. Using the above figure and equations, given that C is 2 microfarad for the 3 different cases of the resonance, what is the proper frequency? Determine the resonance frequency F of R and deduce its period and the circuit's inductance. Verify that U and I are in phase. Enjoy your day and enjoy physics.